Hi everyone, my name is Jiaming Shen. Today it's my honor to present our triple dub work named TaxoExpan Self-supervised Taxonomy Expansion with Precision Enhanced Graph Neural Network. This is a joint work with Microsoft Research, and unfortunately, due to the COVID-19 situation as well as the time zone difference, I'm not able to do the presentation and answer audience questions in real time. If you have any question, please kindly send me an email and I will address your question as soon as possible. So now let's start. So what is a taxonomy? Taxonomy is a hierarchical structure of concepts. If you ever submit a camera-ready version paper to the ACM Digital Library or scan through an e-com website to purchase some products, you have already encountered a taxonomy such as the ACM CCS taxonomy or the Amazon product taxonomy. Those taxonomies can benefit many knowledge-rich applications, and because of its usefulness, people have spent millions of dollars, tens of years to construct a taxonomy. Such a manual construction process is obviously very expensive and time-consuming. Therefore, many automatic taxonomy construction methods are proposed to build a taxonomy from a set of concepts entirely from scratch. Meanwhile, as we all know, human knowledge is never static. It is constantly growing. New concepts will appear every day, and the existing taxonomy may quickly become outdated. Therefore, the dynamic expansions of an existing taxonomy are in great demand. So in this work, we study the following taxonomy expansion problem. We are given an input existing taxonomy and a set of new concepts, and we are expected to output expanded taxonomy that includes all the new concepts. Take the following figure as an example. We are given a computer science field of study taxonomy as well as a set of new concepts, and we want to output an expanded taxonomy that include all the new computer science concepts. Okay, so before I discussing the concrete method, I want to emphasize three parts in our problem formulation. First, in this work, we assume each concept will have a textual name. Therefore, we can get the initial feature vector of each concept in the existing taxonomy, as well as the initial feature vector of each concept of each new concepts based on their textual names. Second, we do not attempt to modify the existing taxonomy. We recognize that the taxonomy modification is useful and necessary in some scenario, but that happens much less frequently and usually require high cautiousness from human curators. So we leave it to the humans. And third, we focus on finding the parent node of each new concepts. This is because we assume the parent node of new concept will appear in the existing taxonomy, but that typically did not hold for the new concept's children. Okay. So to tackle the taxonomy expansion problem, there are three general approaches. First, you can combine the concepts in the existing taxonomy with the new concept set, and then just run the taxonomy construction pipeline from scratch. However, this approach cannot guarantee the newly constructed taxonomy will be exactly the same as the old ones, and those existing relations might be changed, which can cause the instability of its dependent application. For example, if a recommender system uses some feature developed based on the taxonomy, and you just change the taxonomy structure entirely, those features may no longer exist, and your trained recommender system may be broken. And the second possible approach is you can extend the previous WordNet expansion method. However, this approach is not always available since those WordNet expansion method may rely on the uniqueness of the WordNet syntax structure. That is, it requires the syntax structure to be work. But in your domain-specific application, those syntax structure may not be there, so you cannot using the previous method. And thirdly, you may apply some more generic taxonomy expansion method, which typically can be further categorized into two types, supervised method and unsupervised method. However, those supervised methods usually require massive human-labeled training data, and that may not exist in the real applications. And for those unsupervised methods, they typically need some external resources, such as query log, search engine API, and paraphrase dataset. If those external resources are not available, you might not be able to run their methods also. So in these studies, we want to develop a more general method for the taxonomy expansion. Particularly, we develop a self-supervised taxonomy expansion framework that will generate training data from the existing taxonomy and learn the model based on the generated self-training data. Okay, let's start. In our TaxoExpan framework, we model the taxonomy as a Bayesian network, which means given the model parameter theta, the probability of a taxonomy is factorized into the product of a collection of factors. And each factor is the conditional probability of a node given its parent node set. With this formulation, the taxonomy expansion problem will be transformed into the following optimization problem, where we're trying to find a taxonomy with the largest probability that covers all the concepts in the existing taxonomy, denoted as n superscript 0, as well as all the new concepts, denoted as C. Okay, so however, this formulation has two limitations. First, the search space of all taxonomy structures is too large to optimize. And the second, there's no guarantee the relations in the existing taxonomy are kept unchanged. So that may not be good. And therefore, in TaxoExpan, we reduce the previous optimization problem in two steps. First, as we do not attempt to modify the existing taxonomy, we will fix the parent node of each existing concept and only search the parent nodes of each new concept. Second, we assume all new concepts are independent, and thus we can find the best parent node of each new concept independently. So this will give us C-independent optimization problems, where each problem focuses on a single new concept. Okay, we do recognize that such a problem reduction will let us ignore the possible interactions among new concepts, but we'll leave that to the future work that we are currently working on resolving these limitations. And to solve the above C optimization problems, we still need to answer the following two remaining questions. First, when the model parameter theta is given, how can we model the conditional probability of a node given its parent node? Second, how can we learn the model parameter theta without massive human label training data? To answer the first question, we develop a matching model based on position-enhanced graph neural network. To answer the second question, we develop a self-supervised training scheme based on the given existing taxonomies. So in the following, we call this N9 the query concept, and its parent the anchor concept. We call it anchor because if you just think you put the query node under this parent node, the parent node will essentially be the docking, the anchor of this query concept. Okay, so let's start with the first part, the matching models in the TaxoExpan. So the matching model returns a score for each given query anchor pairs, and this score will indicate how likely the query concept is the parent of the query concepts. And there are two key ideas in our matching model. First, we try to represent the anchor concept using its ego network. In short, it's EgoNet. So this EgoNet will capture the surrounding neighborhood information centered on this the anchor concept, that is the ego node. The second idea is that we want to add the position information into this EgoNet. And this position information is the relative position of each node in the anchor concept's EgoNet relative to the query concepts. So what does this mean? Suppose we are given a query concept called high dependency unit, and we try to predict whether this query concept should be placed under this blue node, the anchor concept hospital room. And suppose we put this query underneath this anchor concept, then these three orange nodes, intensive care unit, low dependency unit, operating room, those three nodes will become query concept siblings. And similarly, these two purple nodes will become query concepts grandparents. So that is what I mean by the relative position information. Okay. With these two key ideas, we developed the TaxoExpan's matching model to include three different modules. The first module is the graph propagation modules, which obtain the individual node representation. And then a graph readout module try to aggregate each node's individual representation to a vector that summarizes the information in the entire EagleNet. Finally, given the anchor representation and the query concepts representation, a matching module will be used to predict the final matching degree between the query concept and the anchor concept. Okay, then let me discuss each module in depth. First is the matching modules. Is the graph propagation modules. So in the graph propagation module, we adopt two standard graph neural network architecture, namely the graph convolution network (GCN) and the graph attention network (GAT). Okay, both architectures share the same core propagation mechanism. That is, the node use feature vector in the case layer is the weighted sum of its neighbors transform the node features from the previous layer, passes through a nonlinear activation function. These two architectures, GCN and GAT, they differ in how the weight, this relative weight alpha, is calculated, but they share the same propagation mechanism. So in TaxoExpan, we incorporated the relative node position information using the position embeddings. Particularly, for each node in each layer, we will concatenate its position embedding P with its original feature vector H, and then multiply the concat vector with an enhanced transformation matrix W, which concatenated with the matrix O. So this matrix O is introduced to capture the transformation on the position embeddings. So in such a way, both the node semantic information and the position information are captured. We refer to such position-enhanced GCN and GAT as PGCN and PGAT. The second module is the graph readout module, which aggregates each individual node feature to the graph features. We developed two possible readout methods. One is the weighted mean readout, where each node's weight depends on this node position information. And the second readout method is the concatenation readout, which essentially first average all the nodes embeddings. First average the embeddings of nodes that have the same positions, and then concatenate those averaged node vector to the final graph representation. And finally, with the graph representation and the input new query concepts representation, we use the matching module to calculate the final matching degrees. Specifically, we tested two different architecture. The first one is the multi-layer perceptron, which concatenated the query concept representation with the anchor concept representation and passes through a feed-forward network to predict the final matching degree. And also the log bilinear model, which using a bilinear interaction matrix to capture the interaction of query and anchor. Okay. So we want to emphasize that the anchor concept representation AI is actually query independent, which means you can pre-compute and cache those anchor representations. And this can lead to significantly boost on the inference time. Finally, we name our matching model as follows. You have three subphrases to describe the entire matching model. The first part indicates which architecture is used for the graph propagation module. And similarly, the second part indicates which module is used for the graph readout module. And the third one is for the matching modules. Okay, so there's one remaining question. How can we learn those model parameters without relying on the massive human labeled data? So that's come to our second part, the self-supervised learning method. So we will generate a self-training data from the existing taxonomy and use those self-training data to learn the matching model's parameters. One very intuitive approach for generating self-supervision data is that you just random select one node from the existing taxonomy. You treat it as the query node. Then the true parent position of this query node, as well as its local subnetwork, together with the query node, will give you a true example. So here, the true parent node is node 3, and you get its ego net paired with the original query node. This is a positive query anchor ego net pair. To generate negative pairs, you can randomly select one node that is neither the true parent of query node nor the descendant of the parent node. You randomly select one false position, and then again you get its local subgraph paired with the query node. This gives you false examples. And with those positive and negative pairs, you can optimize your matching model with the binary cross entrophies, and you can just train it. This is one possible approach. However, we find a much better way to do the self-supervised learning in our work. So specifically, we will first generate pairs of a query concept and anchor concepts ego net, as described in the last slides. And then we group those pairs into different training instances, where each training instance will have exactly one positive pair, and all the rest pairs are negative. And all the pairs in the same training instance will share the same query concept. For example, here I show two training instances. For each training instance, there's a multiple pairs, and all those pairs share the same query concept. And exactly one pair is the positive pair. All the others are the negative pairs. Similarly for the training instance use. Then, given those training instances, we optimize the following info-NCE loss. So this loss is essentially the cross-entropy loss of classifying the positive pair out of n possible choices correctly. And those matching scores serve as the model predicted logits. Okay, so this is the our optimized loss. And why we want to optimize this loss? First, empirically, we find it's more robust to the label noise than the previous binary cross-entropy loss. Second, theoretically, this function optimized using this info-NCE loss has the following good properties. That is, the matching degree between the anchor AI and the query NI is proportional to the likelihood of the anchor concept AI divided by its prior. And based on these properties, we will have the following results. That is, given a query concepts NI, the posterior of a candidate anchor position is proportional to the matching degree of this anchor with the query times the prior of the query concept. Since the prior of the query concept is the same across all candidate anchors, that means ranking all anchor concepts based on their posterior probability is the same as ranking those anchors concepts based on their matching degree with the query. And therefore, at inference time, given a new concept, you can simply calculate the matching degrees of all existing concepts in the taxonomy with this new concept. And then you just select the concept with the largest matching degree as this new query concept's parent. So that is a pretty nice properties. To summarize, our TaxoExpan framework did the following three parts. First, we generate the self-supervision data from the existing taxonomy. Second, you choose the specific architectures for three different modules, and you can train the models using info-NCE loss and the generated self-supervision data. I want to pause here for a second. So can you still remember what this name PGAT, WMR, LBM means? Okay, so this means using the position enhanced graph attention network for the graph propagation module, using the weighted mean readout as the graph readout module, and using the log bilinear model as the final matching modules. Okay, then let's start with the experiment. We test our method on 3 datasets. The first 2 are called MAGCS and MAGFU. They are sampled from the Microsoft Academic Graph. And the third one called semi-eval, which is the previously benchmarked dataset for taxonomy expansions. And their statistics are summarized in this table. And we compared with all sort of methods on these 2 datasets. For the first 2 datasets, we compare with unsupervised method called closest parent and closest neighbor. That is, given a new concept, we try to find a node in the existing taxonomy which is most similar to the query concepts based on the embedding similarity. That is the closest parent. And for the closest neighbor, that is for each node in the existing taxonomy, we get its embedding vector by the average of all its neighborhood structure, based off all its neighbors' nodes. So that is essentially the enhanced version of closest parent, considered the neighborhood structure. And for the self-supervised method, we test the following 3 baseline methods together with our proposed TaxoExpan. We first generated the self-supervision data, as I described in the previous slides. And then the distant XGB boost is that we extract a set of feature, manually extract a feature, and feed it to the gradient boosted method. And for the parent MLP, that is, you concatenate the node feature of a candidate parent node with the query concepts, and then you pass it through a multi-layer perceptrons. And the deep set MLP is that you take the average of a candidate parent's parent, that is the grandparent of query concepts. You take the average embedding vector of that, and you concatenate with the candidate parent's position embeddings, and then you concatenate the potential children node of the candidate parents. Finally, you concatenate with the query concepts. Using an all sort of vector concatenate together, you pass it through a multi-layer perceptrons. So essentially, the deep set MLP is the enhanced version of parent NLP with the neighborhood structure considered. On the semi-eval dataset, we compare with another different set of methods. So that include the original top 2 winning solution. The first one is called F-word FS, which means the first word, first sense. So the reason this method worked pretty well is because on the semi-eval dataset, each query concepts will have its associated definition sentence. And the first word, first sense method is essentially find the first word and the first sense of the first word in that query concept's definition sentence. So that turned out to be a pretty good heuristics, and as well as the MSKU method, that's the winning solutions. And the current state-of-the-art method on this dataset is called ETF, and more specifically, it's the ensemble model of ETF with the first word, first sense heuristics. And we will compare with this method using our TaxoExpan framework, as well as the ensemble model of TaxoExpan with the first word, first sense heuristics. Okay, all the code and the dataset are available in the following link. And we evaluate different methods using following evaluation metrics. On the MAGCS and MAGFU dataset, we use the mean rank, that is the rank of the correct position. The smaller the number is, the better the performance is. The other 2 matrix is the hit at 1 and hit at 3, as well as the scaled MRR. Those are typical like ranking evaluation metrics. The higher the number is, the better the performance is. Finally, on the semi-eval dataset, we're using the original competitions evaluation metrics that include UNP accuracy, recall, as well as the FE metrics of the previous 2 metrics. Okay, so let's see some results. First, we test the overall performance on the MAG-CS and MAG-Food dataset, and we can see the following result. First, the closest neighbors method performed better than the closest parent, and the deep-set NLP method outperformed the parent MLP, which shows that modeling neighborhood structure of the anchor concept is very important. Second, you can see that all the self-supervised method can outperform both unsupervised method. That shows generation of self-supervision data for model training is very useful. And finally, the TaxoExpan can outperform all the previous methods. That shows the effectiveness of our proposed approach. And the similar result you can see on the semi-eval dataset. The TaxoExpan ensemble with FWFS achieved the current state-of-the-art method. And in fact, you generated some self-supervision data for model training. Even for the distant XGB boost method, it can outperform the previous two winning solutions. That further shows the generation of self-supervision data is very important. Third, we do more an abbreviation analysis of model architecture on the MAG-CS dataset. So in the below table, the first column is the model index. And if you compare model 2 with model 1, model 4 with model 3, you can see that in general, the graph attention network for the graph propagation seems perform better than using the GCN. And if you compare model 4 with model 2, model 3 with model 1, you can see that the position information can help the graph propagation module a lot. Similarly, if you compare model 5-6 with model 3, model 7-8 with model 4, you will see that the position information can help on the graph readout module. Finally, you can see the last four method, 9 to 12, can outperform model 5 to 8. That shows the log bilinear model perform better than the MLP method. We choose the best four model variants in this table, that is model 7, 8, 11, 12, and we train it using the previous binary cross-entropy loss. And we compare with model trained on binary cross-entropy loss with the model trained on our proposed info-NC loss. And you can clearly see that the info-NC loss is much better than the binary cross-entropy loss training. Finally, we show the efficiency and the scalability of our proposed method. You can see the TaxoExpan can scale linearly to the amount of self-supervision data, and it has pretty good inference time speeds. So predict for almost 2,000 queries on the GPU take less than 20 seconds. Finally, we did some case studies on the MAG-CS and MAG-Food dataset, and you can see that our method can correctly predict the true parent node of query concepts. Finally, we want to summarize this work. In this work, we studied the taxonomy expansion task that is given an existing taxonomy and a set of new concepts. We expand the existing taxonomy to incorporate all new concepts. And we propose the TaxoExpan framework that generates self-supervision data from the existing taxonomy and train a matching model based on the self-supervision data. And as a conclusion, we find that model the neighborhood structure of anchor concept is very important, and the select effective self-supervision training scheme is also very important. Finally, I want to discuss some future work of these studies. First, we are exploring how to consider the insertion order of adding a set of emerging concepts. Maybe we can first identify the taxonomic relations among this new concept set, and then we can generate an appropriate insertion orders. Another direction we are studying is that we may conduct synonym-aware taxonomy expansion. When a new query concepts come, we may first decide whether this new concept is actually the synonym of some other existing terms in the taxonomy. If it isn't, then we predict its parent node. Finally, we are studying how to do the self-supervised taxonomy refinement task. And we may apply the TaxoExpan model on the existing taxonomy and try to identify the potential errors in the existing taxonomy and to fix those errors. That is an interesting future work. And thanks for your attention. If you have any question, please send those questions to my emails and I will answer it as soon as possible. Thank you.